So in this particular lecture, we will have a look at the non-ideal effects of the MOS model. So to begin with, if I have an ideal behavior of a MOS transistor, for example, and if I pick an NMOS transistor of a length, the channel length less than 1 micron. So let me pick a value. Let's say if I'm using a 65 nanometer technology node, I will have the effective channel length to be around 50 nanometers. So if I pick that particular channel length, ideally, this is what we should get. So ideally, I will, I'll just use my pointer so that you'll be able to see this. So ideally, I am talking about this three particular current profiles when we draw it or when we probe it after applying the VDS voltages. Right, so this is what the ideal behavior or the current equations which we have derived in the last couple of lectures. That's what we will get. So a linear profile initially, and then followed by the saturation profile. But actually, when I have a transistor, an NMOS transistor of let's say 65 nanometer channel length, which is effectively, I'm talking about the 50 nanometer channel length. And if I probe it using some kind of a probing meter, I will get this kind of a profile. So I'll get a current profile which is kind of a linear line, and then in the saturation region, it will not be saturated, but there will be a slope. There will be a linear rise even in the saturation region, right? As compared to that of a an ideal behavior, I will get a constant straight line. And here I will get a slightly increasing profile. All right. If I actually compare between the two of the current profiles, on one side we have an ideal IV characteristics, on the other side we have a non-ideal IV characteristics. So if I compare, there are 3 points that are kind of different from each other. One is, if I pick a VDS value, if I pick a particular VDS value, VDS value, the current value for a particular VDS value turns out to be less for a non-ideal IV characteristics, right? So when I compare the right hand side and the left hand side, if I pick for a particular VDS value, the current value is less. The second thing is, if I pick a particular VGS value, right, one particular VGS value or a VGS2 value here, right, and on the left hand side also a VGS2 value, again the current value will be less, right? And if in an ideal behavior, if I increase from VGS1 to VGS2, right, my current equation says, especially the saturation current equation says that it is VGS minus VT the whole square divided by 2. Right, so an increase in the VGS is going to give me proportional to the square of the increase in the VGS. Right, so the current is increasing by square amount, whereas in this particular on the right hand side, the non-ideal IV characteristics, the increase in the current, which I have denoted it as delta 2 here, and here it is delta 1, the delta 2 increase is not as high as that of delta 1. So that is the second the major difference. The third major difference, as I had stated, and I reiterate, after reaching the saturation point, in this particular ideal IV characteristics, we will get a constant line. Right here, after reaching the saturation region, we will not get an ideal constant line. In fact, in the saturation region, it is going to have a linear slope. So moving ahead, so what we had seen in the last slide was, two IV characteristics. One, we stated it as an ideal behavior. The another one is a non-ideal behavior. And to attribute the non-ideal behavior, we attribute it into three phenomena. So one is the velocity saturation, another one is the mobility degradation, and then third one is the channel length modulation. So what do you mean by the velocity saturation? So in an ideal characteristics, the velocity carriers, the velocity of the so let me get this particular pointer. So the velocity v in an ideal characteristics, v is directly proportional to in an ideal characteristics, v will be directly proportional to the electric field, EDS. Okay, for some reason this particular color will not be okay. So the mobility in an ideal characteristics is constant, right? So an increase in the EDS, right, which is which is possible with an increase in the VDS, an increase in the EDS is likely to increase in the velocity of the majority carriers. But what the non-ideal behavior says is the velocity ceases, or there is a resistance to increase with the EDS. With a continuous increase in the EDS, the velocity doesn't increase linearly. Rather, it ceases to increase. Hence, we can expect a lower current, right, for a higher VDS. Right, in an ideal characteristics, as the VDS kept on increasing, we used to get a higher IDS value. But in a non-ideal characteristics, due to the short channel, the non-ideal characteristics are always seen in a shorter channel where the channel length is less than 1 micron. So in that case, what happens is the velocity ceases to increase with a very high increase in the EDS. So remember, another thing is, EDS is a parameter of the channel length. So for a same VDS value, for the same potential difference, right, a smaller channel length is likely to have a very large EDS value. So that's why this effect is observed very highly in the short channel, and that's why it is also called as non-ideal effects or a short channel effects. Right. So in that case, if the velocity ceases to increase further as the electric field increases, the expected value of the current we may not be able to reach. The second is the mobility degradation. So the carriers, while they are actually moving from the source to the drain, the majority carriers, they actually get because of the very high electric field. Because of the very high electric field, now this electric field is coming from the vertical electric field. So VGS value. So I'm talking about the EGS, the gate to the source. So the vertical electric field. Right. Now this vertical electric field is likely to have an effect on the majority carriers which are passing from the source to the drain side. So the source to the drain side will have a lot of scattering effect because they collide at the oxide interface, and also it will have some collisions within the channel itself, and thereby the progress of the majority carriers which started from source to drain is been delimited. Hence, due to that particular effect also, we have a lower IDS value, lower current than expected for the higher VGS. Right, again, this is due to the electric field EGS, which turns out to be very, very high. As the channel length reduces, the thickness is also reduces, for when we are fabricating the transistor itself. As the channel length decreases, the T oxide also decreases, and thereby the electric field, the vertical electric field is likely to be very, very high, giving some kind of a scattering effect. Right, so for a VGS, for a higher VGS, we will not be able to get a larger IDS, whereas in an ideal behavior, we used to get, the current was proportional to the square of the VGS value. Third one, the channel length modulation. So channel length modulation is nothing but in a short channel. If I keep on increasing the VDS, so in this case, let's say that the body is grounded. The source is also grounded for an NMOS transistor, and I'm going to connect this VDS. So if I keep on increasing the VDS value here, this particular depletion region is going to increase. The depletion region is going to increase. All right. So effective channel length is going to decrease. All right. And then we had seen that the current that is drawn out of the transistor is inversely proportional to the channel length. So what is likely to happen is that as the VDS keeps on, the depletion region or the barrier region keeps on increasing due to the higher VDS value, thereby my IDS current is going to increase, right? So that's why we see even after reaching the saturation region, we have a slight increase in the IDS value. Right. So what the scientists or the researchers have done is once they have they fabricated the short channel transistor, NMOS transistor, as well as the PMOS transistors, and identified the current for the different values of VGS and VDS, and empirically they established the mobility value, the effective mobility value, which is now dependent on the VGS value, right? Which is dependent on the different VGS value that we apply, both for PMOS as well as the NMOS. So this is an empirical expression, right? So the expression says 540 centimeter square per volt second divided by, in the numerator we have 1 plus VGS plus VT, and remember this is plus VT, right? It is not minus VT, it is plus VT, divided by 0.54 volt per nanometer. And then the reason is T oxide, here it is actually, it should be mentioned in nanometers. So if the T oxide is 1.05, right, so you have to write 1.05 here and not 1.05 nanometers, because this is already, the empirical formula already takes in voltage per nanometer, right? Similarly, for the effective mobility of the PMOS, or in this case it is holes, this one is electrons, the mobility of the electrons in the NMOS, and this is of the holes, we have 185 centimeter square per volt second divided by 1 plus mod of VGS plus 1.5 VT. So remember that this is VGS is negative, this is also negative, right? So this is also negative, so that's why a mod is taken, so that out of this mod we'll get a positive value. And again, the T oxide should be written as if the T oxide is mentioned in nanometers. Right, just as an example, so now we have an empirical formula for calculating the effective mobility of the holes and effective mobility of the electrons. So for a typical values of a 65 nanometer technology node, if VGS is 1 volts and VT is equal to 0.3 volts, T oxide is 1.05 nanometers for a 65 nanometer technology node, I'll get around 36.37 centimeter square per volt second for the as an effective mobility of the holes. And similarly, effective mobility of the electrons turns out to be 95.7 centimeter square per volt second. So remember, I think we had in our initial lectures we had taken the value of 80 centimeter square per volt second, and we had taken the value in case we have or we haven't, so it is 40 centimeter square per volt second. We used to take approximate, saying that the mobility of the holes is exactly half that of the mobility of the electrons. But to be precisely correct, for a 65 nanometer technology node, using the non-ideal behavior or the short channel current or the short channel effects, we get the mobility of the holes as 36.37 and the mobility of the electrons as 95.7. Right, so that is kind of very important values that we will use from here on. And as we had seen that, as we keep on increasing the electric field for a short channel transistor, the velocity ceases to increase. So at some particular, as we keep on increasing the electric field here, the electric field here is nothing but the lateral electric field, the drain to source electric field here. And if we keep on increasing it, the velocity increases linearly initially, and after a critical point, it is going to be a saturation value. So beyond which we will not have any further rise in the velocity. And the velocity of the electrons is given as the velocity of the electrons in the NMOS is given as 10⁷ centimeter per second, and the velocity of the holes in the PMOS is given as 8 × 10⁶ centimeter per second. So the majority carriers in the NMOS and the PMOS, the velocity in a short channel in a transistor model can reach up to 10⁷ and 8 × 10⁶ centimeter per second respectively. So that is the saturation velocity that has been given. And Looking at this particular graph, or actually determining from this particular graphs, the empirical formula for the velocities at different electric fields is actually given by this particular expression. So before the critical electric field, we have one particular equation, and after electric field we have another equation. After the critical electric field, we know that the velocity is going to be constant, so we have the velocity saturation after when the electric field is greater than or equal to the critical electric field. And if it is less than the critical electric field, we have mu effective, whether it is holes or electrons, multiplied by the electric field divided by 1 plus electric field divided by the critical electric field. Now note here that the critical electric field for the holes and that of the electrons are different. So the blue line emphasizes on the holes velocity, and the red line emphasizes on the electrons velocity. So if looking at this profile, we know that the critical electric field for the electrons reaches earlier than that of the critical electric field of the holes, and it will have some kind of an implications on the current, right? So which we are going to look at it later. So if this is the velocity profile, we know that this is what the velocity profile looks like for electric field less than the critical electric field. So for a very low electric field here, I can actually take out this particular expression as 0, because E will be very, very low compared to EC. So I will have velocity is nothing but equal to effective mobility into the electric field. Now this one is nothing but very, very close to that of what we have been using in the long channel, right? So the long channel current model uses the velocity is directly proportional to the electric field, and that's what we have been using. At the point E is equal to EC, we have two equations, and both of these equations, the overall profile is a continuous profile, and at E is equal to EC, both the equations will satisfy because the profile is continuous, so both the equations should follow the continuity. And if we do that, E is equal to EC in both the equations, what are those both equations? One is velocity is equal to velocity saturation should be equal to that of the velocity which is given by this linear expression of mobility, effective mobility multiplied by E, and then divided in the denominator we have 1 plus E by EC. And if I put E is equal to EC in both the expressions, we are going to get velocity saturation is equal to nothing but mu effective into EC divided by 2. So critical electric field turns out to be a function of course, the mobility, the effective mobility, and that of the velocity saturation, right? So twice into velocity saturation divided by effective mobility is what is the critical electric field we will get. Okay, so let's just to conclude with an example. We have can we determine what is the critical okay, let me get this. What is the critical electric voltage? Critical voltage, which is actually derived from the critical electric field multiplied by the channel length. And what is the critical voltage for the PMOS and NMOS transistor? So this Vc of N is nothing but the VDS, the voltage applied across the drain to source, the critical voltage for the NMOS, and then we have the VDS, the critical voltage applied across the drain to source for the PMOS. Right, so in this case, the critical electric field, so because of this particular formula, we know that for the electrons, the velocity saturation is 10⁻⁷, and for holes, it is 8 × 10⁶. So putting those values, I should be able to find out what is the critical electric field, and from that, we should be able to find out what is Vc of N for a 65 nanometer technology where the channel length is 50 nanometers. So effectively, we are getting the voltage. If I apply 1.044 volts across the drain to source side, I should be able to get the critical electric field and the velocity saturation, right, for the NMOS. And similarly, if I apply 2.1996 volts, I should be able to reach to the critical electric field of the PMOS, and then the velocity saturation of 8 into 10 raised to 6 for the holes. So conclusion, for a lower voltage, just for the lower voltage for the NMOS, if I apply a VDS of 1.044 volts, and if I apply 1.044 volts across the PMOS transistor and across the NMOS transistor, we know that the NMOS transistor will get saturated at 1.044 volts. Whereas for the PMOS, it will still not be a velocity saturated. It needs 2.1996 volts so that it can get velocity saturated. So what it implies is, the PMOS transistor, will still be able to get an increase in the current. So the current, only when it reaches to the 2.1996 volts, I will get the saturation. So the saturation of the velocity. Right, so that's what I've written here. The PMOS is not as badly velocity saturated as NMOS. NMOS reaches the velocity saturation at an earlier voltage than that of the PMOS.